Hello, everyone. So starting from the last point, we just stopped at this slide here. So starting from the demonstrating video of the DC machine, so I could find a way how to include the computer sound in the recording. So let's start from this point.
Hi and welcome back to my YouTube channel. Have you ever wondered how DC generator works? And what are the basic parts of a DC generator?
So guys, we will start here with the concept of the DC generator. And the DC generator or DC motor is just the reverse of the power flow. So the same concept will be also for the DC motor. So I'm going to comment on the video, and I'm going to stop the video and make the comments with you guys just to elaborate more to understand, to allow you understanding the concept of the DC motor as well.
This video will give you the answers to these questions. We will start with the basic parts of the elementary DC generator. As you can see, the configuration of DC generator is pretty simple. The stator is a fixed part of the DC generator. The stator consists of permanent magnets, two of them north and south poles, which is placed to fit around the rotor. The main function of the stator is to provide the magnetic fields through which the rotor or armature coil is rotated. Armature loop are generally placed in slots of armature core. The armature coil is formed by connecting several loops in the series. Armature winding is formed by connecting several coils in series.
So guys, now the loop has two conductors, and if we have many loops connected together, so we call it coil. And if we have the coils connected together, so this is going to form windings. Okay? So this is how our armature windings are going to be formed. Here we will not discuss the field winding because we consider that we have permanent magnets in this configuration. Okay? So let's continue.
The armature loop cuts the magnetic field, due to which an electromotive force, EMF, is induced in it. The split ring is a movable device used for reversing the polarity of the current. It's made of copper. The ring is divided through the middle into two parts. We must use the split ring to achieve single direction of current. The brushes are made of carbon. These are rectangular block-shaped. The only function of these carbon brushes of DC generator is to collect current from commutator segments. A galvanometer is an analog electromechanical actuator that produces a rotary deflection of some type of pointer in response to electric current. So how does the DC generator work? Firstly, we don't want that current direction to change. We want it to remain the same at all times. Let's say in this direction. So, how do we do that? Now, to make sure that the current direction remains the same, what we require is that these brushes constantly keep changing contacts between these wires for each half of rotation. So if the current flows in this way, in this position, this brush must be connected to this wire. So current flows like this and comes out. But when the coil rotates, you can see that when the coil comes to this position, the direction of the current changes. If we want to keep the current in the same direction, we must this brush to be in contact with this wire. Right. And then again, when the coil comes to this position, again the direction of the current changes, and again we want this brush to come in contact with this wire. Probably we already learned that. For every half rotation we must change contacts between brushes and wires. But how do we make this process happen automatically? We can automate this process by adding split rings. Split rings, as the name suggests, is a ring that is split in between, giving two half rings with the same gap in between. Now let's see how the split rings automatically change contact for every half a rotation. So right now this brush is in contact with this half part of the split ring, violet color. When the coil rotates and comes to this position, the direction of the current changes, and this brush now is in contact with the other half part of the split ring, pink color. This arrangement provides that current flows in the same direction. Again, as the coil comes to this position, finishing another half a rotation. You can see that this is only changed contact. Brush is in contact again with the violet color half part of split ring. In this way, the DC generator is built, where the current only flows in one direction through any external circuit, and in this arrangement, with brushes and split rings, which helps us to automatically change contacts, we call them commutators. So split rings act like commutators. The next thing we must mention, that it's really important for working principle of DC generator, is how can we determine the direction of the current, magnetic field and force. To determine all this, we must use Fleming's right-hand rule. So we will explain how can we use Fleming's right-hand rule. As you can see, the rotation of the coil is clockwise, and the force acting on part of the coil AB pushing that part of the coil upwards. So to know the direction of the induced current, we apply the Fleming's right-hand rule. How do we do that? We place our right hand so that the thumb points up, showing the direction of the force. The index finger or the finger pointing in direction of the magnetic field from north to south pole, and middle finger will point in the direction of the induced current, which is in our case from A to B. Similarly, to find the induced current in a part of the coil CD, we again use Fleming's right-hand rule. So the rotation of the coil is clockwise, and the force acting on part of the coil CD pushing that part of the coil downwards. The thumb points down, indicating the direction of the force, indexed finger or for the finger pointing in direction of the magnetic field from north to south, and the middle finger will point in the direction of the induced current, which is in this case from C to D. So to conclude, the induced current follows the path ABCD of the coil. The effect of the split ring commutator in DC generators is to ensure that the induced EMF is always in one direction. We can see that in this graph, where V represents the amount of induced EMF and T represents time. You will notice in the graph how the sine wave changes with rotational speed of the coil.
So here, guys, I just would like to comment with you. So this waveform is the voltage at the terminals of the brushes, which means now we have DC. So since the polarity is positive, we didn't go to the negative side, so this is considered as DC. It's not a pure DC, which means it's not constant value, but this because you have an angle between the conductor while moving and the flux. So when the conductor is in the middle, it will have the peak value, and when it goes far from the magnetic field current will, the magnetic field or the induced volt will reduce until being at the edge or the top here. So it's going to be like in parallel. So having parallel conductor with the magnetic field, this would produce zero EMF. So this would be at this instant here, okay? And then the other conductor will continue the other half cycle, okay? So this is, we call it, by the way, rectified half wave, rectified volt, okay? Rectified DC volt. Okay. Take care that this is the polarity and magnitude of the volt due to just one turn. Okay. So if we have many turns, so this would add the EMF of the one turn together because it's going to be connected in series. And again, this is the volt across the outside brushes, not the inside or as the commutator side. So this is at the outside of the machine terminal. Okay, let's continue.
The coil in this case has clockwise rotation. Increased rotational speed of the coil increases the amount of induced EMF. The induced EMF has a positive sign. Also, you see the example how the sine wave changes with rotational speed of the coil, when the coil is rotating counterclockwise. Again,
so this is one more important note, guys. When you see that by increasing the speed, the voltage magnitude has been increased. So there is a relation between voltage and speed, and we will see that when we discuss the speed control of DC motor. So voltage and speed have a direct relation. Okay, and actually it's going to be a linear relation, and we will see that in our motor speed control later on.
Again, the increased rotational speed of the coil increases the amount of induced EMF. In this case, the induced EMF has a negative sign. To conclude, the DC generator has many advantages like the design is simple, simple to operate, highly reliable, constant voltage can be achieved, speed control is easy.
So, guys, here we have actually the 5 advantages of the DC machine. Design is simple, so you can make it, by the way, using very simple materials. Simple to operate, as you can see, it's not complex in operation. Highly reliable, so reliability is high. So I'm not sure if you learn the reliability course or not yet, but there is one topic called reliability. This is very important topic actually. So the more elements you have in your system, the lower reliability of your system. So since we have very limited number of elements inside our system, so the reliability is relatively high. Constant voltage can be achieved, so we can have a constant volt, and speed control is easy because it's going to be like a linear operation as we discuss later on the speed control. Okay, so I'd like to just go back a bit in the to show you one thing regarding the force and current. So can you imagine here, guys, we have actually the generating mode, which means we have a prime mover that already moving this winding. But if you have instead a source of current, so the source of current will be connecting the conductor here, and you will have the north pole and south pole, which means the flux is moving in this direction. And due to every inductor, so if you have current flowing in this direction, for instance, and the polarity of the current, if the current is flowing direct inside the page like that, okay, in my direction of the cursor to the top like that. So in this case, guys, the flux direction will rotate around the conductor using the right hand or the thumb rule, okay? So from the thumb rule, you will find the flux is rotating around the conductor like that. So from the top side, it will be in the same direction of the flux moving from north pole to south pole. And from the south side, it will be the opposite direction. And this is going to make force to move the inductor in the same force direction you can see here. Okay, so this is due to connecting plus sign at the left-hand side and moving current inside like that. And since the current in the same winding from B to A is going to be moving from B to A, so the force is going to be in the opposite side. So this is, again, will make the motoring operation of our machine. Now, we can return back to our slides. Yeah, so let's continue from this point here, guys. So again, we understood the concept of the commutator and the brushes, and we understood that the commutator along with brushes together are working as a rectifier. So the voltage across the winding inside the machine is going to be AC volt. However, due to the commutator and brushes, so both together will help to commutate the volt or rectify the volt or convert the volt to DC. Okay. So let's, guys, see the analysis of the voltage across our winding we had in the previous slide. So as the rotor moves at a velocity v, if we assume like linear motion, in a magnetic field B, so the voltage will be generated across the conductor AB, the first conductor. So this is going to be V, which is the speed, times B times L. So again, this is for our conductor AB. Okay, so this is AB conductor, just one conductor here. Okay, so the induced volt is going to be V times B times L, where L is the length of the AB conductor. So we can say that the induced volt between terminal BA or on the conductor EBA volt is going to be V times B, which is the magnetic field density times length of the conductor. This is positive into page under pool face and 0 beyond the pool edge. So as we mentioned, if you go to the edge of the pool, you will have 0 EMF, but inside you will have the amount of VB times L. On side BC is 0. The segment is in parallel with B. If we go back to that slide, BC, this is actually in parallel with the flux. So no induced voltage will be applied or will be generated on this part of the coil or in this part of the winding. So the volt is going to be just generated here and here as well. Okay, so this part or the ends of the turn, we will have 0 volt across these ends. Okay, so by the same, guys, we can say EDC is going to be VB times L. So we have now a complete turn, which is going to be summating these voltages together. So we can say that EBA plus EAD plus EDC plus ECB, so all the one turn, it will be just twice the volt, which is 2 times VBL. And this is going to be the shape across the one turn. So this is from A, let's give me, so this is from A to D. Okay, so I can say this is E from A to D. And this is a shape. But take care that this is across the one turn, not across the brushes. Across the brushes, so we expect that this is going to be converted from negative to positive because of the commutator. So in this case, guys, if we convert our motion from translational motion to rotational motion, because now the conductor is rotating, so instead of having speed V, we can replace that by omega R, where omega is the rotational speed and R is the radius of the rotation. So we can say now E equals, replace V by omega R. So we have 2BLV. So from the previous page, we have 2 times B times L times V. So V will be replaced by omega times R. So here we have 2 RLB omega. And you have 2 RL can be replaced by AP divide pi. So this is actually depend on the dimension and the coil cross-section area. So the area, guys, equal half times surface of cylinder, which is going to be pi times R times L. So we can replace that here by AP. So it's going to be 2 divide pi times AP times B times omega. And this is going to be the induced volt under the pool faces. And this is again the induced volt on just one turn. Okay. So if you would like to replace the flux density times area by flux, so this is going to be 2 divide pi times flux times omega m. So this is now the relation of the induced volt. So the induced volt is going to be 2 divide pi times flux times omega m. Okay. Now, if we consider that we have slip rings, this would be the induced volt. But if we consider the commutator, this means our induced volt is going to be commutated to be positive like that. And now if we consider just E of one turn, so this is going to be the shape. But if you have many turns connected together in series, and everyone has a phase shift for sure because all of them are not going to be in the same slot. So in this case, you would have a lot of induced voltages added together. And adding these voltages together, guys, this is going to produce this shape of volt now. So we have few ripples, okay? But this is going to be the summation of many turns together. So having many turns, and then the many turns can produce coil, and the coils together can be considering a winding of the machine, the armature winding, so we can have smooth DC volt coming from the DC machine. So this is, guys, how the voltage across the windings will be in the DC machine. Now, assume that we have just two poles DC machine. So how can we make the two poles now? So you will have winding across the top part of the ferromagnetic material and winding across the bottom part, and connect the windings. So this is going to be connected together and to the DC supply to produce the north and south pole. And then this is going to be the shape, guys. So here we have the slots, and as you can see, the windings are coming from these slots. And here is our commutator. So the commutator here is made of like many strands like that, and the windings are soldered on these strands here. So this is the commutator part. And by the end, the brushes are going to be connected to these this commutator from the top and bottom, for instance. And this is the shape of the two-pole one. In case of four poles, guys, so you would have like four poles like that inside the machine. Okay, now, just remind you again, what is the, how can we construct the winding of the machine? So this is called one turn. So the turn has two conductors. So we have here two conductors. Many turns together form a coil, and many coils together connected together are forming the winding of our machine. Okay, so this is how we can construct the armature winding inside the machine. Now, you know that, guys, most DC machines, particularly larger ones, have more than two poles. So most of the armature conductors can be in the region of high air gap flux density. For a full four-pole DC machine, we will have what's called theta mechanical. So what is the relation between theta mechanical and theta electrical? So the relation, guys, is theta mechanical is the mechanical degree and theta electrical is the electrical degree. The relation is the theta electrical equals P divide 2 divide theta mechanical, where P is the number of poles of the machine. Okay, so P is the number of poles. So P divide 2 times theta mechanical equals theta electrical. Okay, so where P is the number of poles of our machine. So the distance between the centers of two adjacent poles is kept as pole pitch or pole span. So one span pitch equals 180 electrical degree, which is nothing but 360 mechanical degree divide number of poles. So this is now going to be our flux or in flux across the complete cycle. So as you can see, we have two cycles of flux with one complete electrical cycle or one complete mechanical cycle of motion in case of having two pair poles like that, okay, or four poles. Okay. Now, guys, how can we make the windings of a DC machine? There are two well-known techniques of making the windings. the very well-known two techniques are called lap winding and wave winding. So the two sides of coil are placed in two slots on the rotor surface. The distance between the two sides of a coil is called the coil pitch. So the coil pitch, guys, is the distance between the two sides of the coil. So coil will be in the right side and the other part of the coil gonna be in the left side. So this or in between them, this is gonna be called the coil pitch. So the DC armature winding is mostly made of full pitch coils. Two kinds of interconnection are called lap winding and wave winding. How can we make the lap winding and wave windings? So if this is conductor number one, or the first part of the coil number one, the second part of the coil is going to be connected to number two here. If you connect the end of coil number one to the beginning of coil number two, and the end of coil number two to segment number three, so this is called lap winding. This is called lap winding. So as you can see now, coil number two, the beginning of coil number two in slot number two, and both coil number one and coil number two are under the north pole. And here, the end of coil number one and the end of coil number two are under the south pole. So this is called lap winding. In the lap winding, guys, the finish of the first coil is going to be the beginning of the second coil. Let's see the other shape of winding. So here, for instance, this is coil number one coming from pole N, and this is coming to pole S. But instead of starting the second coil under the same pole, like what we have made here, no, we are going to make it in another pole like that. So the shape of the wave or the shape of the winding is going to be like wave. Okay, it's going up and down like that. So we call this as wave winding. Okay, so this is called lap winding and this is called wave winding. What are the benefits? So here, guys, for instance, in lap winding, the number of parallel paths, A, is always equal to the number of poles. So if you have, for instance, a machine of 2 poles, so number of parallel paths will be 2. If you have a machine of 4 poles, number of parallel paths will be 4, and so on. So this is the first type. It's called lap winding. Okay. In the wave winding, since all of the time you will have 2 parallel paths only, so number of parallel paths is going to be 2. So as a conclusion, the wave winding, we will have just 2 parallel paths, and the lap winding, we will have the number of parallel paths equal to the number of machine poles. Okay, so what would be the benefit, guys? The benefit will be how the current and voltages are going to be distributed across these coils. So one of them is going to have higher current and one of them is going to have higher volt. And the higher current would produce higher torque and the higher volt would produce higher speed. So it depends now on the application. So here, for instance, lap winding is used for high current application. Why? Because we can have the coils in parallel, so the current total is going to be increased. Because by the end, every coil can support a certain amount of current. So if we have 4 coils connected in parallel, so the end current here is going to be 4 times the current coil. So IA here equals 4 times I coil, because coils are identical. So here we would have 4 I coils. But take care that the volt of the coils is going to be less than the other type of winding, which is wave winding. So we do prefer the lap winding in low voltage application and high current application. High current means high torque as well. So the application that requires high torque, we do prefer the lap winding. However, in the application that require high voltage, which is going to be reflected to high speed, so we do prefer to make wave winding. Why again? Because the number of parallel paths is going to be just 2 parallel paths, which means our coil is now going to be connected in series instead of parallel. So the total amount of current is going to be just here 2 I coil all of the time, and the voltage is going to be doubled. So this is used for high voltage application and low current application. Let's go back again to the armature voltages, guys, to produce a relation for our induced volt. So we end up in the previous slide that the induced volt equals phi times omega divided pi times number of poles. So this was the last relation we could reach in the previous slides. So this is, guys, for just one induced voltage E for our coil. This is the induced voltage across our coil. So the voltage induced in all turns connected in series across the positive and negative brushes will contribute to the average terminal volt E. So if you would like to get the average volt now, so you should multiply the average volt, sorry, the induced volt times N divide A. So N is going to be the number of the total number of the armature winding, okay, total number of turns, and A is the number of parallel paths. So this is going to be the relation now. E equals N divide A times the total induced voltage, which is phi P divide pi times omega M. So in this case, we can say that EA, or the armature induced volt, equals NP times phi omega divide pi A. Again, N is number of turns, P is number of poles, phi is the flux, omega is the motor speed, mechanical speed, pi is constant, and A is number of parallel paths. So how many constants we will have now for our motor? If you see that for any motor, guys, when you control the motor speed, you will not change the number of turns. So the motor is already wound. So this is constant. Number of poles in the motor also is going to be constant. We are not going to change the number of poles during operation. Pi is constant, A is constant. So all of these parts, guys, can be considered as constant. So let's define that as Ka, which is the machine or the armature constant. So Ka is the armature constant. Okay. So we can say that the induced volt equals Ka times phi, which is the flux, times omega M. Again, where K is known as the armature or the machine constant. And the machine constant is given by NP divided pi A or ZP divided 2 pi A. What is the difference between Z and N? So N is the number of turns, Z is the number of conductors, because you know that any turn will have 2 conductors. So this is the first shape that we discussed. This is conductor AB, and this is conductor CD, and by the end, the part BC and the part AD will not have any induced volt. Only the effective conductor that will have induced voltages are AB and CD. So we can say that one turn equals 2 conductors. So N all of the time equals 2 times Z, where Z is number of conductors. Okay, so you can say that Ka, the constant, the machine constant, equal ZP divided 2 pi A. Okay, so this is the machine or armature constant of the DC motor. Again, guys, I'm just reminding you about the principle of the DC motor. So if this is the field coming from N to S and you have the conductor inside, what will happen is the conductor itself, when it is supplied by electrical current, there will be a flux around this conductor. So assuming that the current is coming out of the page like that, so the flux around the conductor will be in this direction. So the total flux on the top will be less than the flux in the bottom. So this is going to make force to the top like that. If the current is reversed, so this means the current is going inside the page. So this is here the dot. Dot means current out of page, and plus means in of page. So this is going inside the page and this is going outside of the page. Okay, so in the page, this means if you apply the right-hand rule, you will find the flux is moving in this direction. So this is going to increase the flux on the top, reduce the flux on the bottom, because the flux on the bottom is going to cancel the main flux direction. Okay, so by the end, the total flux lines on the top will be higher than the total flux lines on the bottom, and this is going to make a force to the bottom side. So this is the concept of the motoring action across the conductor. And again, remember that for any conductor, that conductor will be, or the two conductors will not be under the same pool, so which means this is going to make opposite force directions across the two conductors in the same turn, and this would make opposite force and what's called torque inside our machine. So starting from the force again, to find the relation of the electrical torque and the electromechanical torque that we have in our DC motor, so we can say that the force equals BLI, where B is the flux density, L is the length of the conductor, and I is the conductor current. We can say that the conductor current as a relation of the total armature current, you know that the conductor current is nothing but the total current divided number of baths. So we can say BL times IA divided number of baths A, where IC is the current in the conductor and IA is the total armature current. So now if we would like to get the torque as a function of force, so the torque developed by the conductor is F times R. So the force of or across the conductor times the radius of rotation. So the average torque developed by the conductor can be calculated as the force, which is BLIA divided A times R. So BLRIA divided number of parallel paths. Substituting B relation, you know that B equals phi divided the cross-section area under pool. So this would be now phi divide the area, and the area is 2 times pi divides R, L. So in this case, guys, you will find the relation by the end is pi times P times IA divided 2 pi A, where pi is the flux, P is number of poles, IA is the current, total armature current, 2 pi times A is the number of parallel paths. So this is the relation of torque as a function of current. So the total torque is going to be now twice of the conductor torque. So we can say that torque of one turn equals 2 times torque of conductor. And if we have a coil of N turns, so the total amount of torque is going to be 2 times torque per conductor times number of turns. So we can end up with torque equals N pi P divided pi A times IA. And again, we end up with this relation And this relation is defined before as the machine constant or armature constant. So we can say that torque equals Ka times phi times Ia. Remember that we said before that EMF is Ka times phi times omega m. And here we end up with torque equals Ka times phi times Ia. If we consider K as a constant, and flux, if we consider the flux is constant in the machine, so we can say that torque is directly proportional to electrical current, and EMF is directly proportional to machine speed. And this is the benefit we have from DC machine, the direct relation between torque and current and induced voltage and speed. Okay, so by the end, we can say that this machine is very easy to be controlled. Why? Because the direct relation between torque and current and speed and induced voltage. In case of motor action, the electrical power input to the machine is going to be EA times IA. The magnetic field by the electrical system must be equal to the mechanical power, which is torque times omega m, developed and withdrawn from the field of the mechanical speed. So therefore, we can say that induced voltage times IA equals Ka phi times omega times Ia. So we just substituted the value of EA here by Ka phi times omega. So we can end up with Ka phi times Ia equals torque. So we can say this is torque times omega. And this is, guys, the relation of the developed power. So P developed equals either EA times IA or T developed or torque times omega m. And this is called the developed power or the electromechanical power that is developed inside the machine. Okay, guys, we will have some other losses inside the machine. We'll discuss that in the power flow of the machine later on, but this is called the developed power of the DC machine. So the developed power again equals electrically equals EA times IA, the excitation voltage times the armature current, or equals the developed torque times the motor speed. We have here, guys, an example. We will end up with this example here to just understand the concept of the machine windings and the armature constant of the machine. So we have here a 4-pole DC machine has an armature current with a radius of 12.5 centimeters and an effective length of 25 centimeters. The poles cover 75% of the armature periphery. So this means, guys, only 75% of the area is covered under pole. So we should multiply the area times 0.75 to get the effective area. Then the armature winding consists of 33 coils, each coil having 7 turns. So number of turns can be considered now 7 times 33. So this is going to be the number of turns. You need to multiply this times 2 to get the number of conductors. The coils are accommodated in 33 slots. So the machine has 33 slots. And the average flux density under each pole is 0.75 Tesla. So this is the P value that we have in this machine. First case, in case of the armature is lap winding, determine the armature constant Ka, determine the induced armature voltage when the armature rated at 1000 RPM, determine the current in the coil and the electromagnetic torque developed when the armature current is 400 amperes. Finally, determine the power developed by the armature. This is in the first case if the armature is lap winding. And then repeat all from A to D in case of wave winding. So let's, guys, start step by step. Let's start with the lap winding. So lap winding again. So we have the armature constant Ka equals N times P divide pi A. We can replace N by Z divide 2. So Z P divide 2 pi A. And Z can be calculated as 2 times 33 turns, 33 coils times 7 turns. So we have 462 conductors in our machine. In case of lap winding, you know that the number of parallel paths equals number of poles. So we can say for lap winding here, since the machine is 4 poles machine, so we will have 4 parallel paths. So we can say that Ka equals Z, which is number of conductors, times times number of P, which is 4, divide 2A times pi. So we can end up with the flux constant, the machine constant equal 73.53. Now, the second part of the question is determine the induced armature volt when the armature rotates at 1000 RPM. We got Ka and we need to get the armature volt if the RPM is 1000 RPM. So, firstly, we need to figure out the effective area of our machine. So this is the length of our rotor. This is the length of our rotor and length of our conductor. And this is, the cylindrical shape, and we have a radius R of this machine. So we can get the pool area as 2 pi times, let's get the values from here. So we have here the radius R equals 12.5 centimeter, which is 0.125 meter. So the radius is 0.125 meter. So we can write down here, this is our radius. And we have also the length of our conductor. The effective length is 25 centimeters. So L equals 0.25 meter. So this is the length. And if you would like to get the effective area, so the effective area is going to be the area of circle times length. So the area is going to, sorry, not the area, the perimeter of the circle times length. So this is going to be the interior area of our rotor. So 2 pi times R times L. Take care that machine is 4 poles, so we have to divide over 4. And take care also that only 75% is covered under pool. So the effective area now under pool is going to be 0.75 times 2 pi RL divided number of pools. If you would like to type the relation here, so we can say the effective area equals 2 pi RL divide number of pools times the effective area. Effective area under pool. So this would be our relation, guys, the effective area under pool. So this is the effective area in square meter. Now we can start calculating our flux. So flux equals the effective area times the flux density. So the effective area times 0.75 Tesla is going to provide 0.0276 Weber. So this is phi. Now we can say the induced volt equals the machine constant times phi times omega. So machine constant we calculated before, it's 73.53 times phi times our speed. Speed omega is in radian per second, and here we have speed in RPM. So in order to convert RPM to radian per second, you have to multiply times 2 pi divided 60 or pi divided 30, the same, okay? So we can get the induced voltage, which is 212.5 volts, okay? So from here, guys, we understood how to calculate the effective area and just substitute now in the relation of the induced volt in order to get the induced volt across our motor. Part C is determine the current in the coil and the electromagnetic torque. So he mentioned here the armature current is 400 amperes. So since we have 4 poles in the in case of lap winding, so we have 4 parallel paths. So we can say one coil will have the armature current divided A, which is going to be 100 ampere. So the torque equals Ka phi times Ia. Ka is calculated, phi is calculated, and Ia is 400 ampere. So this is going to be the torque that we have in this case, which is 811.8 Newton meter. Part D. So here we determine the current coil, so I coil, and the electrical torque, T electrical. Part D, determine the power developed. You know that we mentioned power developed can be EA times IA or equals developed torque or electrical torque times omega M. So you can get it by any way. We already calculated we calculated EA. We have IA equals 400. We calculated the torque and we have omega M equals or speed equals 1000 RPM, so we can get it using this speed. So whatever the way you would like to calculate, so we can say PA now equals EA times IA, so 212.5 volt times 400 volts, so this is 58 kilowatts, or torque equals 811.8 times speed 1000 RPM times 2 pi divided 60, so we would have the same amount of developed power. All of these, guys, is made with lap winding. Now, we need to repeat all of that with wave winding. So wave winding means number of parallel paths all of the time is going to be 2. So in case of wave winding, number of poles is 4, A equals 2, the same number of conductors. So if you start making the calculation, you would find that Ka equals 147.06. Let's compare that with the first Ka. If we go back, Ka here is 73.53. So this affects the machine constant. So the machine constant here is doubled. So since the machine constant is doubled, so we expect to have different values right now. Starting with our speed, so you know that speed is given already 1000 RPM, so just get the same amount of speed. So starting with EA, so EA would be the constant times flux times omega. So in this case, the volt is going to be 425 volts. So the volt is 2 times the volt that we have before, because we connected 2 coils in series instead of having 4 parallel paths. So we have now 2 parallel paths and 2 series connected coils. So this means, guys, here we have twice of the voltages that we have before. What would be the current of the conductor? The current of the coil would be now, if you have the current coil, which is going to be the same all of the time because the coil has a certain impedance and cannot support different value of current. So the current is 100 ampere per coil all of the time. But here we have 2 parallel coils. So this means by the end, the total armature current would be only 200 ampere. So this machine cannot support more than 200 ampere because the coils are connected as wave winding here, which means 2 coils are connected in parallel and two coils in every path are connected in series. So the current is only 200 ampere. This actually would provide different current torque. If you calculate that, you will find the torque here is K times phi times our current, which is 811.8. It's not different. It's the same amount of torque. But take care that the current is different. So torque is 800 Newton meter. Why? Because K is twice, K is doubled, and current is half. So we got the same amount of torque. And the machine speed is still the same. So we got the same amount of power by the end. Okay, guys, so this is here the calculations in case of wave winding. So let's stop, guys, at this slide and continue next class from here. Thank you so much and see you next class.